Imagine robots that don't just, follow instructions blindly, but robots that actually learn maybe better, more efficient ways to do things, even inventing their own shortcuts.
Hmm.
How do we get them past just copying us and really innovating, especially out in the messy, unpredictable real world?
That's the big question, isn't it?
Well, today we're diving into something really fascinating that seems to promise just that. We're exploring vision language action models, or VLA models.
Right, VLAs. They're this powerful new way of thinking about robots, letting them combine what they see, what they understand from language, and what they physically do.
Sounds amazing. But like a lot of new tech, they've hit some snags, right?
Okay.
Especially with the usual training methods.
Oh, definitely. Using traditional approaches like supervised fine-tuning or SFT, we run into a couple of major hurdles. First, there's a huge problem with data scarcity.
Getting enough data.
Yeah, getting enough good data, collecting large amounts of high-quality demonstrations, precise recordings of humans guiding the robot, it's surprisingly hard
Yeah.
and very, very expensive.
You can kind of picture that, can't you? It's not just showing the robot once.
No way.
You need these carefully set up scenarios, tons of different objects for it to handle, and skilled people doing the actions again and again.
And that cost and complexity, it really puts a cap on how much data we can get and how varied it can be.
Which naturally leads to the next problem.
It does, limited generalization. Because the models are trained on these, well, specific and somewhat limited data sets, they often don't cope well when they face something new.
Like a new task or an object they haven't seen.
Or even just a different environment. We call that distribution shift.
Yeah.
And it's a real bottleneck for getting these robots working reliably out in the wild.
Okay, so if you've been wondering how we make robots smarter, more adaptable, well, this deep dive is definitely for you. Our mission today is to introduce you to SimpleVLA-RL. It's this innovative reinforcement learning, or RL, framework built specifically to tackle those challenges, the data scarcity, the generalization gap.
And hopefully push VLA models to the next level.
Consider this your shortcut to getting up to speed on some really exciting breakthroughs in robot capability.
So let's dig a bit deeper into why these problems are so tricky. That data scarcity thing. It's not just about volume.
Right, you mentioned the cost.
Yeah, the whole process of setting up those perfect experiments, making sure you have all sorts of different objects, using skilled operators, it just makes collecting data incredibly expensive.
So it limits the scale and the diversity of what the robot learns from.
Fundamentally limits it. And that ties right back into the generalization bottleneck.
Because it's only seen a narrow slice of the world.
Pretty much. The VLA model gets really good at the specific things it was trained on, but throw in an unfamiliar object, maybe change the lighting, ask it to do a slight variation of a task.
And performance can just tank.
It really can. It's like teaching someone chess, but only letting them play against one specific person. You wouldn't expect them to suddenly beat a grandmaster. Right?
Yeah, makes sense. Where did the idea to use reinforcement learning come from here? Was there inspiration from other fields?
There was, actually. A lot of inspiration came from the world of large reasoning models, LRMs. Think things like DeepSeek R1. Those models showed that RL could seriously boost their ability to reason through complex problems, step by step.
So, if RL helps with abstract thinking.
Could it help with concrete, physical action planning in robots? That was the key question. Could RL unlock that same kind of improvement for VLAs?
And that's where SimpleVLA-RL comes in.
And that's exactly what it was designed for.
Yeah.
It's an efficient RL framework built for VLA models. It actually builds on an existing RL framework called veRL, but with some key adaptations.
Adaptations for robots specifically.
Right, things like VLA-specific ways of sampling trajectories, making it scalable so it can learn faster using parallel processing, handling rendering for multiple environments, and optimizing how the loss is calculated, all geared towards making RL work well for these VLA models.
And you mentioned it uses a different kind of reward system than some traditional robot RL?
Yes, that's a really important distinction. A lot of robot RL uses these complex, hand-designed process rewards, rewarding tiny intermediate steps.
Which sounds complicated to set up.
It is, and often not transferable to new tasks. SimpleVLA-RL, on the other hand, uses simple outcome rewards.
Simple outcome rewards. That sounds almost too simple for tasks like, say, stacking bowls or opening a drawer. How does that actually work? Just success or failure?
Pretty much just that. It's Quite elegant, really. It uses a binary reward, 1 if the task succeeds or 0 if it fails.
So the whole sequence of actions gets a 1 if the final goal is met.
That's right. If the VLA model manages to complete the task, say successfully stacking the bowls, that entire sequence of actions leading up to it gets rewarded with a 1. If it fails anywhere along the way, the whole thing gets a 0.
And the benefit is?
Well, it's straightforward, it scales really well, and it avoids that big problem you get with process rewards where they're often non-transferable. You don't have to painstakingly design rewards for every little step of every new task.
Okay, that makes a lot of sense for scalability. But wait, for RL to work, the model needs to try different things, right? Including things that might fail. How does a VLA model generate those actions when it's interacting with the real physical world? That seems different from how, say, a language model generates text.
It is very different. That's where interactive VLA rollout comes into play. An LLM might just generate a stream of text.
Right.
But a VLA model needs this continuous back-and-forth interaction with its environment. Every action the robot takes physically changes the world around it.
So the next action depends on what just happened.
Absolutely. The next action has to be based on real-time feedback. What does it see now? What's the robot's current physical state? It's a constant loop. Perceive, act, perceive the change, act again.
That feedback loop sounds crucial, but how do you make sure it doesn't just keep doing the same slightly off thing? How does SimpleVLA-RL push it to explore, to find genuinely new or better ways?
That's critical. And SimpleVLA-RL uses a kind of three-pronged strategy to boost exploration. First, there's something called dynamic sampling.
Dynamic sampling. What does that do?
It basically makes sure that during training, the robot always sees a mix of both successful and failed attempts. It deliberately filters out batches of experience where everything succeeded or everything failed.
Why is that important?
Well, if it only sees perfect runs, it doesn't learn why it succeeded versus alternatives. If it only sees failures, it gets no positive signal to reinforce. By ensuring there's always a mix, you guarantee the learning algorithm gets a meaningful signal, what statisticians call a non-zero advantage estimate, which keeps the learning process stable and moving forward. It prevents the gradients from vanishing.
Okay, so it keeps the learning signal strong by ensuring variety. Does that risk filtering out genuinely new but maybe rare failures?
That's a good point. The aim is to strike a balance, not filter all identical outcomes, but ensure enough variety for a good learning signal. And the second strategy helps here too. Adjusted clipping range.
Clipping range? That sounds technical.
It's a common thing in RL algorithms like PPO.
Yeah.
It basically limits how much the robot's strategy can change in one update step. SimpleVLA-RL adjusts this range slightly. Think of it like loosening the leash just a little bit.
To allow for bigger jumps sometimes?
Sort of. It allows for a greater increase in the probability of actions that were initially considered very unlikely, but might have turned out to be valuable, maybe leading to success unexpectedly. It encourages exploring those less obvious paths.
Okay, so dynamic sampling ensures variety. Adjusted clipping range allows for exploring rarer good moves. What's the third part?
The third piece is higher rollout temperature. When the VLA model is generating these sequences of actions, the temperature parameter in the sampling process is turned up.
Like turning up the creativity knob.
Kind of. A higher temperature makes the model's action choices less predictable, more random, more diverse. It encourages the robot to just try more different things, to stumble upon potentially better solutions it wouldn't have found if it just stuck to the most likely actions.
Got it. And the actual learning algorithm underneath all this?
It uses an adapted version of an algorithm called GRPO, which stands for Group Relative Policy Optimization. It's been modified specifically for this setup to, again, enhance exploration and also, importantly, to get rid of the need for a separate reference model during training.
Which makes things simpler.
Simpler, uses less memory, and speeds up the learning.
Okay, that's a lot of smart engineering. But the proof is in the pudding, right? What were the results? Did SimpleVLA-RL actually deliver significant improvements?
The results are pretty striking, actually. Let's look at the LIBERO benchmark, which is quite demanding. An SFT-tuned model started with a respectable 91% average success rate.
Already pretty good.
Yeah, but after applying SimpleVLA-RL, that jumped to 99%, outperforming previous state-of-the-art VLA models. And for the really long tasks in that benchmark, LIBERO long, the success rate went from 86.5% all the way up to 98.5%.
Wow, okay, that's a big leap. What about other benchmarks? Similar story. On RoboTwin 1.0, they saw a 30.6% absolute gain from about 40% success up to over 70%. And on RoboTwin 2.0, which has some very long tasks, performance went from around 38% to nearly 69%. That's an 80% relative improvement.
Those are impressive numbers.
Yeah.
But going back to one of the main goals tackling data scarcity, how did it fare there? Did they test it with really limited data?
They did, and this is possibly one of the most compelling results. They ran an experiment where they fine-tuned a model using just one single demonstration per task, just one example.
Okay, that's barely any data. What happened?
With just that one demo and standard SFT, the average success rate on LIBERO was, well, mediocre, about 49%. But then they took that same poorly trained model and applied SimpleVLA-RL. The success rate shot up to 96.9%.
Wait, from 49% to nearly 97%, with the same single demonstration as the starting point?
Exactly. And get this, that 96.9% is even better than the model trained with the full SFT dataset, which only reached 91% without RL. That's incredible. So RL can more than make up for a massive lack of initial training data. What about the LIBERO long tasks in that scenario?
Even more dramatic. From just 17.3% success with one trajectory SFT, it jumped to 91.7% after RL.
Okay, that really changes the game for how much human effort might be needed up front. What about the other big issue, generalization to unseen tasks?
Here again, SimpleVLA-RL showed clear benefits. The RL-enhanced models consistently perform better on unseen tasks across different variations, spatial changes, new objects, different goals within the LIBERO benchmark.
Compared to just SFT?
Compared to SFT, yes. The SFT-only models tended to overfit. They learned the training tasks well, but when faced with something new, their performance often dropped significantly, sometimes even falling off a cliff, what's called catastrophic forgetting, where success rates hit 0 on unseen tasks.
So RL helps the model become more generally capable, not just memorizing specific solutions.
It seems to build a more robust, adaptable understanding.
Does this hold up when moving from simulation to a real robot? The sim-to-real gap is notoriously difficult.
They tested that too, and the results are promising. Policies trained entirely in simulation using SimpleVLA-RL were transferred directly to real robots for tasks on RoboTwin 2.0.
With no extra real-world training data.
Correct. No real robot data used for the RL training itself. And they saw an average improvement from 17.5% success with SFT alone up to 38.5% with the RL train policy.
That's a solid improvement in the real world. Any specific task examples?
Yeah, like the stack bowls task, performance went from 32% with SFT to 70% with RL. And on a pick bottle task, where the SFT model completely failed in the real world, the RL model achieved a 15% success rate. Still room for improvement, but it shows RL helped achieve a level of precision SFT couldn't manage.
You know, what really catches my attention in all this is the idea that the robots aren't just getting better at tasks we show them, but might actually find new ways. I heard about something called pushcut. Is that related?
Pushcut is the perfect example of that. It's this really interesting emergent behavior they observed during the RL training.
Emergent, meaning it wasn't programmed in?
Not at all. It describes how the VLA model, through exploration driven by RL, learned new, often more efficient ways to interact with objects, ways that weren't present in the original human demonstration data.
Okay, give me an example. How does pushcut work?
Sure. On RoboTwin 2.0, there's a task called Move Can Pot. The human demos always showed the robot doing a sequence. Grasp the can, move the can, place the can in the pot. Standard stuff.
Right.
But the model, trained with SimpleVLA-RL, figured something else out. It learned it could just push the can directly into the pot. No grasping needed.
Ah, it found a shortcut.
Essentially, yes. Another example was place object A next to object B. Again, demos showed grasp in place. The RL model often learned to just push object A into the correct position relative to B.
That's genuinely fascinating. The robot is optimizing beyond the human examples.
It really is. It highlights how RL, driven purely by that simple outcome reward, did the task succeed or not, can push the model to explore and find novel, sometimes more efficient strategies. It's fundamentally different from SFT, which is mostly about imitation.
It's like the robot having its own little aha moment.
You could definitely call it that. It really parallels discoveries seen in other advanced AI models where they find non-intuitive but effective solutions through self-learning.
This sounds incredibly powerful. Are there limits? Does SimpleVLA-RL always work, or does it need something to get started?
There are definitely limitations, failure modes we need to consider. The big one is the initial capability of the VLA model before you apply RL.
Meaning?
If the base model, maybe after SFT, has absolutely zero ability on a task like a 0% success rate, maybe it was trained with 0 trajectories, or just couldn't learn anything from the few it saw.
Okay.
In that case, RL fails completely. Because if the robot never succeeds, it never gets that positive reward signal of 1. It only ever sees 0 or
So there's nothing for the reinforcement learning to reinforce.
Precisely. It needs at least some successful examples in its exploration phase to learn from. There's a threshold. You need a minimal level of competence for RL to latch onto and improve.
Is there data backing that up?
Yes. The researchers found that a model starting with a baseline from 100 SFT trajectories gained about 18% from RL. But a model starting from a stronger baseline of 1,000 SFT trajectories gained over 22% from RL.
So a better starting point allows RL to achieve even more.
It seems so. A stronger initial model provides a better foundation for exploration, leading to potentially larger gains from the RL phase. If the starting point is too weak, the exploration might not find enough success, and the RL improvement could be minimal.
Okay, so we've really covered a lot of ground today. From the core challenges robots face with learning, getting enough good data, generalizing to new situations.
Right, those bottlenecks of data scarcity and limited generalization.
To how this framework, SimpleVLA-RL, uses reinforcement learning, specifically with simple outcome rewards and clever exploration techniques to overcome those hurdles.
And achieve some really state-of-the-art results on tough benchmarks.
Yeah, the performance gains were impressive, especially that experiment showing massive improvement, even with just one initial demonstration. That really hits home the potential to reduce reliance on massive human data sets.
And not just improving on known tasks, but showing better generalization to unseen ones, and even successful transfer from simulation to the real world.
Plus, the whole push-cut phenomenon, robots discovering their own, more efficient ways to do things, that feels like a glimpse of truly adaptive intelligence.
Absolutely. Understanding frameworks like SimpleVLA-RL, it really gives you a window into the cutting edge of making robots genuinely more intelligent, more autonomous out there in the world. It's about letting them learn and discover beyond just copying what we show them.
So thinking about that, given that SimpleVLA-RL allows robots to spontaneously discover these more efficient push-cut behaviors, what other unforeseen optimal strategies might autonomous learning unlock for us in complex real-world challenges we haven't even conceived of yet?